next one will be slightly different. And you can add sophistication to the model by having the directions not just be parallel or anti-parallel, but slightly different. Dr. Donovan, did you have a paper in mind that you knew about that talked about doing the Ising model?
Ising model, I don't right now, but I can look. I had not a paper, but an appendix in a textbook, if I remember right, that implemented it. I'll look again and see if there's a paper.
Okay. I had a group of students 20 years ago do this project as a parallel processing thing. And it didn't work. The model worked fine, but the parallel processing never worked up to what it should have. We were able to, with parallel processing, to always slow down the computing time. But we were using a 1,000 by 1,000 by 1,000 array.
That's a lot.
That's a lot. So we can measure the times pretty easily with our watch.
Yeah.
So what you want to do is to look at properties of the domain formation and then just the ferromagnetic properties in general to see if you can see hysteresis, other properties of ferromagnetism. But I think that I remember a paper somewhere on this that we used, but I couldn't find any of my notes on that project. So I'll keep looking. If you can look, we'll send you something today or tomorrow.
Okay.
To get you going.
So is the Heisenberg model for the magnetic interaction a different model than the psi function, or? Sure.
Well, it uses basic quantum mechanics, but it's a model that looks at the probability for a particle aligning itself with the magnetic field as opposed to opposite the magnetic field. And it takes into account that there are atoms around it that have their spins in particular directions. So it's not just a random process. There's an interaction with the 6 local atoms in a cubic array that you would have around you.
And why is it called Ising model?
The fellow's name who came up with it was Ising.
Oh.
I-S-I-N-G.
I thought it was I-C-I-N-G.
No. Matter of fact, he was pretty famous for several things in statistical mechanics. And when Harvard found out he didn't have a PhD in physics, they had to give him one so that they didn't have to take his salary away from him. So anyway, we'll get that to you. And then if you've got some questions about doing it, there's a lot of data taking here, and the programs are not quick to run. They might be with a 10 by 100 by 100.
Now maybe. Now, Minji, what do you like to program
in? I'm really not good at any programming so far. Probably Mathematica is the easiest for me.
Mathematica?
But 3D array, I guess Mathematica cannot really handle. So
it can handle it. It'll be probably slower than MATLAB, but
MATLAB was set up for matrix work.
If you take advantage of the matrix.
Yeah.
way of multiplying. But yeah, so have you done any MATLAB and other projects?
I have done a couple MATLABs, but I'm still trying to get familiar with that. And I guess this project can really help me to get better at it if I use MATLAB.
Yeah, you have to get good at it in a hurry, but it doesn't use a lot of difficult ideas from programming language. So
let's see.
And the rolling dice that you mentioned, is it something similar to Gaussian that we did, or?
no, what it is there's a random function that you can call, and it gives you a random number between 0 and 1. And that's rolling a dice, right?
Yep.
And if your probability is for something to happen is 25%, then you say if the random number comes back between 0 and 0.25, the event happens. If the random number is from 2.5 to 1, then the event does not happen. So that's what I mean by rolling the dice to see if something happens. You're using a random measurement and your probability to construct an algorithm for whether the event happens or not.
And it usually uses something called a Monte Carlo method.
Yeah, so you'll naturally back into this Monte Carlo approach to your program without knowing it.
I think. Let me see if I can find it for.
And wasn't one of the main characteristics of ferromagnetism is that the magnetic field kind of aligns?
Say that again?
Isn't one of the main characteristics of ferromagnetism is that the array we're looking for kind of perfectly aligns with the magnetic field we're interacting with?
That's part of it, and part of it you won't get to know, but it's not just that the atoms align with the field. It's that when they align, they're still vibrating, oscillating, rotating, precessing in the field. You get a coordinated motion between them that enhances the net magnetic field.
So do they also have the nuclear magnetic resonance as well?
No, that's not a. So these are just spins, basically, without any reference to what they necessarily are. Let me see if I can show you the. There's a mathematical demonstration that you can run. Let me see if I can share this. You might want to start there to kind of see what I just downloaded from Wolfram demonstrations. It's gonna be a little bit slow, but we can have various spins. I think the spins here represent up is black, or well, one is black, one is One is up, one is down. Not sure what this is actually. I think it starts off like that and then it propagates down. And this is with time, what's happening, how the spins are changing. And what you see, these regions are essentially domains, as Dr. Peterson was talking about, where spins will align parallel or so up or down. So this is in 2D. So the black, let's call the black up and the brown, the white down. So you'll have different domains where there'll be some alignment of the spins. So you can kind of use this as a guide to, but of course, you know, you'll have to do your own.
It's interesting. So, Dr. P, did you want me to make it more like a vector field sort of a thing rather than that?
No, that's what you want to be looking at right there.
Okay.
But you'll be looking at it in 3D, and the question is, how do you see it in 3D? And so you take if you've got 20 atoms deep, then you're going to have 20
Slices.
2D slices, and you're going to have to animate them so that you can watch the animation back and forth so you can visualize these 3D structures. Say a group of all the blacks, meaning a spin of spin up or spin down, whatever it means for your program, and a blob of all the whites, which is another spin up, spin down. And then you can add the whole thing together to find out what the total magnetization of your sample is for that magnetic field. And then, so you can get macroscopic variables and you can see the microscopic structure. So you add up essentially all the directions of the spins, plus and minus, and you'll have a net value, and that'll tell you your magnetization for that magnetic field. And that allows you then to graph a B versus H curve and look at your look for hysteresis. For instance, if you start off with a 0 B field, you can look what the net magnetization is, and then start turning up the field. And each time, you know, you've got to wait a while to let things settle out, and then you calculate the net spin, and that tells you then the net magnetization, and then you just keep going like that. So it takes a while to generate all this data, and it'll take a little while to think through it. So that's why you want to start getting a program that makes some sense. And this one that Dr. Donev showed you is a good way to.
It may be a good way to start with 2D and then move to 3D.
And I guess they've got the Heisenberg magnetization in there. That has nothing to do with the uncertainty principle.
Not sure what they've got here. Let's see. I don't know what the rules they've implemented on.
Anyway, if you get something to him and I'll get something to him, and then we'll have him on his way.
Okay.
Minju, were you able to log on to the one of the remote computers?
Oh, not yet. I'm gonna try it after this Zoom call.
Well, you need to be learning the lab view, and that's why I was thinking.
Oh, okay.
They're not going to be able to load LabVIEW on your system. It's too new, and they don't have it operating on a Mac yet for system 1015. So this will allow you to get online onto a PC where there's a LabVIEW running, so you can try some of the exercises in that textbook. Did you get the textbook downloaded?
Yeah.
Okay. You don't have to do the whole textbook. Remember, your goal is to try to take data from multimeters and control power supplies. So you want to learn enough, say, out of the first 2 or 3 chapters that you know the language, you know where things are, you'll generally know how to make a program. Then you need to go back and look at how, at the end of the book, how you talk to an instrument. And then we'll have that set up for you to try.
Okay.
All right?
Yep. So it's
There'll be probably new password.
Yeah, I'm going to go in, or not go in, I'm going to change the password here. But which one was working for you just a minute ago?
Let's see. The second one was working. I mean, none of the passwords were working, but the second one was online.
Oh, the password did not work?
Yeah, so we have to. So
Okay.
you have to log in through yours and change the password.
Okay, so let me change the passwords and get them fixed, and I'll send that to you in a few hours.
okay.
All right. You have any other questions?
No, I do not, but I guess I should start studying about the Heisenberg model and the Ising model.
Yeah, the Heisenberg, you're probably pretty much going to take the result. I don't think that you're going to have time to explore too much the details of that model. So that's if we had more time, you might be able to, but we don't. But you're gonna be talking about the magnetic properties of materials. So you do need to go back and look at some of your E&M for that.
And I need to explain that in terms of spin.
Yeah.
What does spin have to do with the magnetic field?
Well, that's a good question. If you've got spin, you've got a rotating charge, don't you?
Yep.
If you've got a rotating charge, you've got a current. You've got a current, it creates a magnetic field. So it has a magnetic dipole moment as a result. So the magnetization is the vector sum of all the magnetic dipole moments.
Remember, though, how we talked about it when we were doing the Earth field NMR, that the way we imagine classically a spinning charge like the electron, it's not really true, because the electron is not a little ball that spins. The quantum mechanical property of spin doesn't have a classical analog. We use it as a kind of a crutch to help ourselves think of it as something spinning, but in fact it's a quantum mechanical feature that doesn't exist in the classical world. So even a single electron has a defined direction of the spin.
So each electron has a magnetic moment, and so the magnetization is a sum of the magnetic moments, dipole moments, which is essentially the sum of all its spins.
Shouldn't the protons also have the same feature?
Their magnetic dipole moments are much smaller than the electrons. So it's the electrons that dominate.
Okay.
Remember that the nuclei are not beyond hydrogen. The nuclei are composed of multiple particles, so their spins might add up to nothing. And the same with the electrons. So some materials are not ferromagnetic because they don't have unpaired spins.
Yeah, he knows that. We just studied that this day before, or
All right. Perfect.
Friday and Monday, adding up all the spins. Even nuclei don't have any.
Are you doing the spin orbit coupling or just?
I mentioned spin orbit coupling for the protons, and that we did a little bit with the electrons, but not much.
Mm-hmm.
More conceptual than
Yeah.
doing the quantum mechanics with it.
Yeah, Ninja, I think, there's lots of information on, I'll try to find a educational paper that's useful, but, in the meantime, you can read, even Wikipedia has a pretty long article about the Ising model.
If you get online at the library here at Swanee and go to journals and go to the American Journal of Physics, you can search it for Ising model and see what you come up with.
Okay.
All right, sir.
Okay.
Let me check and see if anybody else is logged in. One, two, three. I guess that's it. So we'll talk to you again shortly, Minju. I'll get some information to you and tell you what that new password is.
All right. Thank you.
All right.
All right. Sounds good.